Every phone, clock, and schedule agrees. A day has 24 hours, yet no law of physics requires it. So who fixed 24 and why not 10, 12, or 100? The answer winds through ancient night skies, temple courtyards, star clocks, and the birth of equal hours. A day is one full rotation of Earth relative to the Sun, but humans decided how to divide that rotation. 24 hours is a cultural and scientific convention, first split into 12 parts of night and 12 of day with variable length, then standardized into 24 equal hours used in science, transport, and the military. In New Kingdom Egypt, priests used stellar deacons, star groups rising consecutively through the night, to track time. They counted 12 star risings to mark the night and implicitly matched them with 12 daylight divisions, giving a 24-part cycle. These were seasonal hours. Summer daylight hours were longer than winter ones. 12 fit daily life, roughly 12 lunar cycles per year and 12 finger joints on one hand, made counting to 12 practical. Two 12s, night and day, yielded 24. The sexagesimal legacy from Babylonia, base 60, made 12, 24, and 60 convenient divisors for circles, angles, and cycles. Greek astronomers formalized the 24-part day. Hipparchus proposed 24 equal equinoctial hours, fixing hour length to the equinox, so an hour no longer stretched or shrank with seasons. Equal hours enabled precise astronomy, computation, and universal comparison. Scholars across the Islamic world refined instruments and tables for prayer times, navigation, and astronomy. Equal hours became standard in astronomical practice, supported by advances in sundials, water clocks, and mathematical timetables. In medieval Europe, early 14th century mechanical clocks began striking equal hours. Public time shifted from flexible seasonal hours to uniform hours, making commerce, labor, and civic life more predictable and embedding the 24-hour structure in daily routine. Societies favored two 12-hour cycles on dials because they were easier to read and strike, while astronomers and navigators often used 24-hour rings. The compromise persisted. Everyday clocks showed 1 to 12 twice, while scientific contexts increasingly used 0 to 23. The 24-hour day emerged step by step: Egyptian star watches, Greek equal hours, Islamic precision, and European mechanics, later universalized by railways, time zones, and 24-hour notation. No single inventor dictated 24. Civilizations converged on it for practicality, divisibility, and science. Ancient Egypt turned the night sky into a clock. From temple roofs and courtyards, priests mapped star risings to slice darkness into 12 parts, then paired night with day to frame a 24-part cycle. Egyptians identified bands of star groups, deacons, that rose one after another through the night. As each deacon appeared on the eastern horizon, a new watch began. 12 risings completed the night. The sequence shifted slowly through the year with the seasons. Beyond nightly time, 36 deacons also marked the civil year in 10-day blocks, totaling 360 days. 5 extra festival days were added to reach 365, keeping the calendar in step with the Nile's rhythm and the heliacal rising of Sirius. Daylight and darkness were each divided into 12 hours, but their length changed with the seasons. Summer daylight hours stretched long, winter daylight hours shrank. Night hours did the opposite. Hours were proportional, not fixed. Sundials and L-shaped shadow clocks tracked daylight segments by the sun's position. At night or on cloudy days, water clocks, clepsydra, measured outflows against marked scales, turning stellar and solar concepts into practical time intervals. Rituals, offerings, and guard rotations followed the night watches and daylight segments. The star tables and clock marks synchronized priests, workers, and festivals with a shared rhythm that matched the sky. Merchants could reach 12 by tapping finger joints with a thumb, while farmers watched roughly 12 lunations each year. 12 was easy to make, easy to divide by 2, 3, 4, 6, and easy to remember.
perfect for splitting day and night. Egypt's 12 night watches and 12-day divisions influenced neighboring cultures through trade, conquest, and scholarship, spreading the idea that a full day naturally falls into 24 parts. Seasonal hours complicated calculation and long-distance coordination. An hour in Thebes at midsummer didn't equal an hour in Alexandria at midwinter. Astronomy, navigation, and later commerce needed uniform units. By the late classical world, scholars began anchoring hours to the equinox, defining 24 equal segments of the full day. This shift preserved Egypt's 12 plus 12 structure while standardizing length, paving the way for precise astronomy and, centuries later, mechanical clocks. Egypt pioneered the 12-watch night and a mirrored 12-part day, established tools to measure segments, and tied calendar and sky together. Even after equal hours arrived, the shape of the day, 12 and 12, remained. From Deacons to Clepsydra, Egypt gave the day its 12 plus 12 spine. Next, how Greek scholars fixed hours to equal length and why equinoctial hours became the language of precise time.
Seasonal hours were practical for farmers and temples, but confusing for astronomy and calculation. Greek scholars introduced a breakthrough: equal hours that don't change with season or latitude. An hour at midsummer daytime was longer than an hour at midwinter daytime. The same hour varied by location and date, breaking comparisons across cities, voyages, and star observations. Precise astronomy needed a fixed unit. Greek astronomy crystallized the solution. Divide the day into 24 equal segments anchored to the equinox, when day and night are equal. These equinoctial hours detached the hour from seasonal stretch, creating a constant unit for charts, calculations, and instruments. Using the equinox made the geometry simple: 12 equal segments for daylight and 12 for night at that reference date, locking one uniform hour length for the entire year. Greek and Hellenistic craftsmen adjusted sundials and water clocks to display equal hours, at least at the dial's designed latitude. Astronomical texts and tables began listing events in equal hours, spreading the practice among scholars and navigators. With equal hours, astronomers could publish star rising and setting times, eclipse windows, and planetary positions in a format anyone else could reproduce. A shared hour unlocked shared data. For centuries, public life still used seasonal hours, but ports, surveyors, and scholars increasingly referenced equal hours in logbooks, land measures, and ephemerides. Two time systems coexisted: flexible civic time and precise scientific time. Equal-hour geometry entered curricula alongside spherical astronomy. Students learned to convert between seasonal and equal hours, recalibrating sundials and water clocks, and aligning local practice with mathematical models. By standardizing the unit, equal hours paved the way for devices that ticked uniformly. When escapements and gear trains arrived in medieval Europe, a clock could finally strike identical hours because the concept already existed. Equal hours simplified everything that required comparison: star catalogs, navigation legs, shadow lengths, architectural planning, and eventually timetables. A constant hour meant fewer conversions, fewer errors, and better predictions. The Greeks didn't invent 24, they made each part truly equal. Their equinoctial hour turned Egypt's 12 plus 12 into a universal measuring stick, setting the stage for Islamic-era precision, mechanical clocks, and the modern 24-hour world. Say Section 4 to continue with the Islamic Golden Age, astrolabes, Zij tables, prayer time tables, and the refinement of equal hours. From equal hours on paper to equal hours in practice, scholars across the Islamic world turned timekeeping into precision craft, aligning prayer schedules, navigation, and astronomy with a 24-part calculable day. Mosques appointed a muwakkit, the timekeeper, responsible for determining daily prayer times, lunar dates, and seasonal adjustments. His work demanded accurate solar and stellar timing, pushing instruments and tables to new levels. Brass astrolabes solved time from the sun or a known star, converted between unequal and equal hours, and worked at multiple latitudes. With a few sights and a plate swap, the user could find local time, sunrise, sunset, and Qibla direction. Polar-aligned gnomons and carefully calculated hour lines produced dials that displayed equal hours instead of seasonal ones, standardizing public time in courtyards, madrasas, and observatories. Clepsydra evolved with graduated scales, feedback floats, and automata to regulate flow more evenly. Some devices displayed both hours and minutes, signaling a shift toward truly uniform measurement in civic spaces. Comprehensive astronomical tables, Zaj, tabulated solar and stellar positions, sunrise-sunset, lunar phases, and prayer windows in equal hours. Navigators and scholars could now convert times across regions with shared parameters. Daily prayers, lunar calendar months, and Ramadan sighting anchored time to observation and calculation. The demand for reliable dawn, noon, and sunset times helped normalize consistent equal-hour practices across cities. Urban observatories coordinated star catalogs, instrument calibration, and time signals. Their outputs, calibrated dials, corrected tables, and trained timekeepers spread accurate hours along trade and pilgrimage routes. Texts, instruments, and methods traveled into Iberia and beyond. Astrolabes, equal-hour sundial design, and computational recipes. Latin translations placed equal-hour timekeeping next to Greek geometry in curricula. Water-powered astronomical displays in mosques and squares delivered predictable equal intervals, striking or dropping balls on the hour. Civic life began to sync with regular beats rather than seasonal stretch. By normalizing equal hours in religion, navigation, and astronomy, the Islamic Golden Age bridged theory and daily practice. When mechanical escapements arrived in Europe, a culture already thinking in equal hours could adopt them rapidly. Equal hours left the page and entered cities, on brass plates, stone dials, and flowing water. Next, medieval Europe's mechanical breakthrough, escapements, striking hours, tower clocks, and how the 24-hour framework moved into the streets. Equal hours were an idea waiting for a machine. In medieval Europe, engineers built devices that struck identical hours day and night, moving 24 parts from astronomy into streets and squares. Water clocks froze in winter and drifted with temperature. Sundials failed at night and in bad weather. Cities, monasteries, and markets needed a timekeeper that ran continuously and sounded the hour for everyone. The breakthrough was a weight-driven mechanism regulated by an escapement. Falling weights turned gears. The verge and foliate escapement released motion in tiny steps, producing the first steady tick-tock and enabling uniform hours. Monasteries, organized around fixed prayer times, were early adopters. Soon, bell towers in cathedrals and town halls rang the hours for entire communities, synchronizing work, markets, guard shifts, and curfews. Early public clocks were heard more than seen. Bells counted the hours, 1 strike for 1, 2 for 2, and so on. The sound system matched a double 12 culture, 12 strokes twice per day, while still enforcing equal hour length. With bells marking identical intervals, the city's rhythm aligned. Opening times, guild rules, court sessions, and deliveries. Equal hours left scholarly tables and became civic infrastructure. Even before minute pointer spread, mechanical regularity encouraged finer scheduling. quarter-hour chimes, work rotations, and shared meet times. The machine made smaller units imaginable and useful. Early escapements varied with friction and force. Clocks gained or lost time. Craftsmen introduced better gear cutting, adjustable foliates, temperature-aware setup, and periodic resets at noon or stellar transits to keep civic clocks credible. Mechanical hours disciplined urban life. Bells set expectations. Show up, close shop, pay fees, change guards. Clock time began to rival solar time in authority, creating a mindset of measurable, comparable intervals. Know-how spread through itinerant clockmakers, cathedral projects, and royal commissions. Designs converged. Weight drums, going trains, striking trains, and maintenance routines. An ecosystem for reliable, equal hours. Medieval mechanics turned equal hours into a habit the whole city could hear. Next, how portable spring clocks, maritime chronometry, and eventually pendulums sharpened those hours into precision, paving the path to the modern 24-hour world. Equal hours rang from towers, but daily personal time needed something smaller. The next leap was power you could carry, springs replacing heavy weights. Coiled steel mainsprings stored energy without tall drop shafts. No more hanging stones or fixed towers, timekeeping could shrink to tables, walls, and eventually the body. Springs unwind with changing torque. The cone-shaped fusee evened that force with a chain or cord, letting early spring clocks run more steadily across a full wind. Courts and wealthy households adopted spring-driven table clocks that kept equal hours in private rooms day and night. Time left the square and entered the home. Miniaturization produced pendant clocks and the famous Nuremberg eggs. Accuracy was modest, but for the first time, people could carry uniform hours as they moved. A balance wheel with a regulating device replaced the foliate in portable pieces, offering steadier oscillations and less sensitivity to jostling, crucial for watches. Adding a tiny spiral hairspring to the balance locked the oscillation to a near-constant frequency. Overnight, error dropped from tens of minutes to a few minutes per day, making minutes, and soon seconds, practical units. As regulation improved, dials gained minute hands and, for observatories, seconds. Schedules could now reference finer slices of the same 24-hour framework. Portable clocks still drifted. Owners set them by noon marks, sundials, or known time signals. The partnership of machine and sky kept households in step with civic clocks. Merchants timed meetings, craftsmen timed processes, and travelers coordinated departures. Equal hours ceased to be only public. They became personal currency for work and movement. Springs and regulators carried the 24-hour idea from bell towers to pockets. Next, pendulums, precision observatories, and why a swinging weight made the hour so exact that railways, mapping, and science could trust the clock. Mechanical clocks made hours equal. A swinging weight made them precise. The pendulum turned city time into scientific time. A swinging pendulum keeps almost the same period even if the arc changes slightly. This isochronism hinted that a clock regulated by a pendulum could beat with steady rhythm. In the 1650s, a weight-driven clock regulated by a pendulum achieved a dramatic accuracy jump, from drifting by many minutes per day to roughly seconds per day. The age of precision hours began. Clockmakers learned that small pendulum arcs are most stable. The anchor escapement reduced the swing to just a few degrees, improving accuracy and allowing longer, slower pendulums that needed less power and wore less. A pendulum near 1 meter long takes 1 second per half swing. Clocks built around this became tall, long-case instruments, with seconds marked on the dial, turning seconds from theory into household reality. Observatories installed pendulum regulators as reference clocks.
Astronomers time star transits to set local noon, calibrate public clocks, and correct navigational tables, binding the sky to the city's schedule. Metal rods change length with heat, shifting a pendulum's rate. Compensating pendulums and controlled rooms stabilize the beat, keeping precision through seasons. Postal deadlines, factory whistles, and lecture times moved from by the hour to by the minute. Stations posted timetables, courts set precise sessions, and scientific experiments synchronized to second marks. Even fine clocks drift. Timekeepers compared the regulator to the sun at culmination or to star transits, nudged the pendulum length, and posted weekly corrections. Precision as a civic habit. Second-hand spread with standardized dial layouts. Apprentices learned to set beat symmetry, adjust escapement depth, and tune amplitude. Craft rules that kept hours identical from town to town. The pendulum gave the 24-hour day its sharp edges, hours that could be trusted anywhere the ground was steady. Next, the sea problem. Why pendulums fail on rolling ships, and how marine chronometers preserved equal hours across oceans.
On land, pendulums made hours, exact. At sea, they failed. Rolling decks, temperature swings, and humidity ruined the beat. If equal hours could travel across oceans, ships could find longitude, and empires could move on schedule. Latitude comes from the sun's height or the pole star's angle. Longitude is time, the local noon compared to a reference noon. 1 hour of time error equals 15 degrees of longitude error, hundreds of kilometers off course. A ship's motion changes the swing plane and amplitude. Pendulums speed up, slow down, or stop. Salt air, temperature, and lubrication finish the job. Navigators needed a timekeeper that ignored the ship's roll. A balance wheel paired with a spiral hairspring oscillates even when tilted. With careful geometry and a shock-resistant escapement, the rate can stay steady through motion, a foundation for a true sea clock. Metal expands with heat, altering balance and spring. Bimetallic balances and clever regulators counter drift so the rate stayed constant from cold dawn to hot noon, crucial on long voyages. Detached escapements let the balance swing nearly free, touched only briefly each cycle. Jewels, fine pivots, and anti-shock features reduced wear. The goal? Keep the frequency pure no matter the waves. Sea trials compared departure time to arrival time after weeks at sea. A daily error of a few seconds meant safe landfall. Minutes per day meant reefs. Observatory trials later certified the best instruments before they ever saw a ship. Early chronometers were as dear as a small ship's boat. Naval fleets and key merchant routes got them first. As design simplified and production scaled, more vessels carried reliable time, shrinking losses and insurance risk. Sailors checked local noon with a sextant and sun sight, compared it to the ship's reference time, and computed longitude. Night sights on stars cross-checked the arithmetic. Time turned the sky into a map. By the 19th century, chronometers became standard kit for serious voyages. Ports sold time signals, observatories dropped time balls at noon, and ships synchronized and sailed with confidence. A portable, precise hour unlocked longitude. The 24-hour day wasn't just a schedule. It became a coordinate system stretching across oceans. Next, railways, telegraph time signals, and how synchronized hours knit continents into a single timetable. Trains made distance feel smaller, but clashing local times made timetables dangerous. Synchronizing equal hours across cities became a matter of safety and commerce. Before standardization, each town set clocks by its own sun. A traveler could pass through a dozen noons in a day. Schedules slipped, dispatchers misread tables, and collisions grew likelier as traffic increased. Rail networks began adopting a single reference time across their lines, practical, enforceable, and posted at stations. Conductors synchronized watches, station masters reset clocks, timetables finally aligned. The electric telegraph turned time into a signal. Observatories sent daily time pulses along wires so far-flung stations could set clocks within seconds, pulling entire regions into the same minute and second. At first, railway time governed trains only, but businesses, courts, and markets found it simpler and safer. Town halls and churches followed suit. Shopkeepers set their clocks to the station. A single nationwide time worked for small countries. Continents needed stripes. Time zones, each offset exactly 1 hour, balanced geography with simplicity so trains and telegrams could cross mountains and prairies without chaos. On a chosen date, cities reset clocks to the new standard. Many experienced noon twice, once by the old local sun, once by the new uniform time, marking the moment schedules snapped into one grid. Time zone maps printed the new rules. National timetables listed connections down to minutes. Passengers learned to arrive early, rail yards learned to stage precisely, and shippers planned around guaranteed slots. Factories synchronized shifts, banks coordinated clears, newspapers aligned edition times, and schools rang bells to the same beat. Standard time rewired daily life around the shared 24-hour scaffold. Some objected that clocks should follow the sun. Others feared lost daylight or local identity. But the benefits, fewer accidents, reliable connections, predictable business, won quickly. Equal hours became equal everywhere, enforced by rails and carried by wires. Next, the global agreement on the prime meridian, the 24-time zone world map, and how midnight, noon, and date lines were fixed for international use. Railways and telegraphs unified regions. The next step unified the planet. A single prime meridian and a 24-zone map turned local hours into a global system. Longitude needs a zero line. For centuries, maps used different city meridians, forcing conversions. Science, shipping, and cables needed one agreed reference so every clock and chart aligned. By the late 19th century, most nautical almanacs and sea charts already referenced Greenwich. Selecting the Greenwich Observatory's meridian standardized existing practice and minimized disruption to fleets, trade, and telegraph schedules. Divide Earth's 360 degrees by 24. Each zone spans 15 degrees of longitude, offset by 1 hour from the prime meridian. Noon remains roughly when the sun is highest locally, while time jumps in clean, hourly steps across the map. Every civil time is defined as an offset from the prime reference. A port can set +2, +530, or +8 to match geography, trade links, or politics. The system is flexible at edges while stable at its core. When regions switched to standard time, clocks were reset at a coordinated moment, producing 2 noons in one day. That reset signaled the end of local solar time as the public standard. Zones follow people more than meridians. Lines curve around cities, rail hubs, and national borders to keep commuters, businesses, and broadcasters in sync even when geography suggests otherwise. Not every place fits an exact hour. Some regions adopt 30-minute or 45-minute offsets to better match solar noon or social rhythms. The grid allows these exceptions without breaking the system. Global time needs a start and an end. Midnight at the prime reference begins the civil day. An international date line opposite the prime meridian flips the calendar date so the count remains consistent around the world.
Shipping schedules, cable timetables, and newspapers printed zone charts. Schools taught offsets. Businesses listed hours, local plus offset. And travelers learned to carry the grid in their heads. A common 0 and 24 numbered zones turned equal hours into a worldwide language. Next, how radio time signals, speaking clocks, and broadcast pips kept that language synchronized down to the second across continents. Equal hours spanned the globe on paper. Radio made them arrive everywhere at once. Time turned into a signal you could hear, decode, and set by, down to the second. Railways, factories, and ships needed daily correction. A centralized, reliable broadcast let thousands of clocks reset together, shrinking drift and preventing cascading schedule errors. Telephone speaking clocks announced the exact time when you called. Hour, minute, second. Cities adopted them as public services so homes, shops, and newsrooms could align to a common reference. Short tone bursts at the top of the hour, pips, give a crisp, universal cue for studios, dispatchers, and listeners. Tone patterns and voice announcements carried hours and minutes. A final long pip marked the exact second. Low-frequency transmitters covered huge areas with stable propagation. Nighttime reception improved further, so radio-controlled clocks often synchronized after dark, then free-ran by crystal the rest of the day. Shortwave signals spanned continents with modest power. Although path delays varied by milliseconds, that precision was more than enough for civil schedules, industrial control, and lab logging outside metropolitan grids. Early users set clocks by ear. Later receivers decoded embedded time codes automatically. Wall clocks, wristwatches, and lab instruments began to listen at night, wake, sync, and sleep, quietly keeping the household on the world's time. Radio-controlled wristwatches and alarm clocks democratized accuracy once reserved for observatories. A cheap receiver and quartz oscillator delivered second-level precision with no user math and no local observatory. Harbor time balls once dropped at noon to signal ships. Radio replaced the visual cue with an audible one that worked in fog, rain, and over hills. Factory whistles and broadcast studios kept the beat with the press of a button. Studios hit the opening note at the pip. Trains departed on the dot, and news anchors rolled headlines precisely at the hour. Citizens learned to trust the tone more than the shadow on a dial. Radio made the second public. The world now shared not just the same 24 hours, but the same instants. Next, atomic standards. How quantum transitions defined the second, corrected the planet's wobble, and gave the 24-hour day its modern backbone. Mechanical precision and radio signals unified the world to the minute. Atomic physics made the second itself exact, giving the 24-hour day a foundation that does not drift with Earth. Earth's rotation is not perfectly steady. Seasons, tides, and core mantle dynamics make days wander by milliseconds. For navigation, telecom, and science, a second tied to atoms, unchanged by weather or wobble, became essential. Physicists discovered that atoms absorb and emit microwaves at uniquely sharp frequencies. Locking an oscillator to one of these transitions turns nature's fingerprint into a clock, repeatable anywhere on Earth. A particular transition in cesium-133 provides an ultra-stable tick. Count exactly 9,192,631,770 cycles of that radiation, and you have 1 second, defined the same way in every lab, ship, or satellite. The world officially adopted the atomic definition. The second no longer depends on Earth's spin, but on a quantum transition. This froze the unit's length, letting hours and days be built from a rock-solid base. No single device rules time. Dozens of atomic clocks and national labs are averaged into continuous scales. If one drifts, the ensemble stays steady, delivering a smooth global second. Because Earth rotation still matters for civil life, the world's broadcast time keeps atomic seconds but adds leap seconds occasionally to stay close to the sun's day. Civil clocks read atomic precision, solar alignment preserved. Household clocks use quartz for short-term stability and periodically sync to official signals or network time. The result? Affordable devices that inherit laboratory accuracy without the lab. Satellites and fiber networks rely on atomic-derived timing to measure distance, tag data, and align communications. When systems agree to the same second, planes land, packets route, and markets cleared at scale. With a fixed second, an hour is exactly 3,600 of them anywhere, anytime. The 24-hour day used on clocks is now a precise count of atomic seconds, independent of clouds, seasons, or tectonic shifts. Atoms gave the day its ruler. Next, leap seconds, proposals to remove them, and how future optical clocks might sharpen the second again, without breaking the world's 24-hour rhythm.
Atomic clocks define the second perfectly, but Earth rotation wanders. Leap seconds are the tiny stitches that keep civil time aligned with the sun while preserving atomic precision. Earth does not spin like a perfect flywheel. Tides, winds, earthquakes, and core mantle interactions make day length wobble by milliseconds, and over centuries the planet slowly spins down. Atomic seconds stay constant, solar days do not. Civil clocks follow Coordinated Universal Time, UTC, a continuous stream of atomic seconds that occasionally pauses for 1 extra second, so noon stays close to the sun. This keeps daily life, astronomy, and navigation in step. When needed, the last minute of a chosen day becomes 61 seconds long. Clocks read 23:59:59, then 23:59:60, then 00:00. The insertion is rare, irregular, and announced months in advance so systems can prepare. International services monitor Earth's rotation and compare it to atomic time. When the difference nears a set limit, they schedule a leap second, typically at the end of June or December, to pull civil time back toward the sun. A 1-second jump can break software, logs, and networks built for smooth, monotonically increasing timestamps. Some operators smeared the leap by spreading the extra second over hours to avoid a visible step. Broadcast time services announce the pending leap. Data centers roll out updates, exchanges coordinate cutovers, and public clocks either step or smear. The morning after, schedules, trains, and devices continue seamlessly. In principle, if Earth briefly spins faster, a minute could have only 59 seconds to push civil time forward. This has not been required yet, but engineers design systems to handle the possibility. Standards bodies have agreed to phase out routine leap-second insertions in the coming years, allowing a slow drift between civil time and the sun that can be corrected far less often, reducing global operational risk. Your clock's 24 hours count exactly 86,400 atomic seconds most days, and 86,401 on a leap second day. The structure remains 24 equal hours.
Leap seconds only keep those hours near the sun's day for civil use. Leap seconds are the handshake between unchanging atomic ticks and a living planet's wobble. Next, optical lattice clocks and deep space navigation. How even sharper seconds may refine positioning and science without changing our 24-hour rhythm.
Atomic time is steady. Now it gets sharper. Optical clocks count light oscillations hundreds of trillions of times per second, turning the second into an even finer ruler without altering the 24-hour structure. Higher frequency ticks mean more subdivisions per second and less fractional error. Where microwave cesium counts billions of cycles, optical standards count hundreds of trillions, shrinking noise and drift for the same averaging time. Ion clocks trap a single charged atom and probe an ultra-narrow transition with exquisite control. Optical lattice clocks trap thousands of neutral atoms in a laser egg carton, average them together, and reach extreme stability quickly. Trapped light normally shifts atomic energy levels and ruins accuracy. Tuning the lattice laser to a special magic wavelength cancels the shift, letting atoms keep a pristine ticking frequency while held nearly motionless. Best optical clocks keep time so well they would slip about 1 second in tens of billions of years under lab conditions, orders of magnitude beyond traditional cesium standards used to define the SI second. Relativity says clocks lower in gravity run slower. Optical clocks are so sensitive they detect height changes of centimeters by tiny frequency shifts, opening relativistic geodesy to map Earth's gravity from time itself. Improving the second's realization doesn't change daily life units. An hour remains 3,600 seconds and a civil day 24 hours. Optical clocks simply realize those seconds with far less uncertainty for navigation, networks, and science. Metrology labs compare many optical clocks worldwide by fiber links and satellites. When the community agrees comparison is robust and reproducible, the SI second will likely transition from cesium to an optical definition. Transportable optical clocks already ride in vans and labs on carts, supporting telecom timing, tectonic studies, and cross-checks of national timescales. Each generation shrinks lasers, vacuums, and control electronics. Positioning. Tighter timing improves satellite navigation and multipath correction. Networks. Denser, faster data links with cleaner synchronization margins. Science. Tests of fundamental physics, dark matter searches, and gravitational wave timing auxiliaries. Optical clocks sharpen the second that underpins the 24-hour day, but they don't change the day itself. Next is how computers and the internet distribute these perfect seconds: NTP, PTP, and the time that lives inside packets. The world now runs on networks. To make logs line up, trades settle, and videos stream, computers must agree on the same second. Internet time protocols distribute the 24-hour day to every device. File systems, databases, security tokens, and audits all depend on correct ordering. Milliseconds can decide whether a trade is valid, a login is accepted, or a sensor event is trusted. Clock drift breaks causality. A device asks a trusted time source for the current time, measures round-trip delay, estimates offset, and slews its local clock gently to match, avoiding jumps that could confuse software timers or schedulers. Network Time Protocol organizes sources in strata. Primary servers anchored to atomic, GNSS, or lab references, secondary servers fan timing to the public and enterprises. Clients pull multiple servers, filter outliers, and converge on a stable average. Clients query several sources, reject inconsistent answers, and weight the most stable. Clocks are disciplined slowly.
The local oscillator is nudged, not reset, so timestamps remain monotonic and applications stay calm. Authenticated modes protect against spoofing. Operators pin to trusted servers, run internal relays, and monitor offsets and jitter. Good hygiene, multiple sources, authentication, and monitoring prevents single-point failure. Precision Time Protocol adds hardware timestamping in switches and network cards to remove software delay. With boundary and transparent clocks, local networks can align to microseconds for automation, finance, media, and grid control. Enterprises mix GNSS receivers, radio terrestrial feeds, and upstream time services. A few Stratum 1 servers feed campus PTP grandmasters and NTP relays. All endpoints converge on the same UTC-based second. Operators either step at insertion or smear by spreading 1 extra second across hours to avoid a visible jump. The choice is documented so distributed systems process events consistently. Dashboards track offset, jitter, and frequency error. Alerts fire when drift exceeds budget. Service level objectives specify, for example, plus or minus 100 microseconds for trading cores, plus or minus 1 millisecond for media, or plus or minus 10 milliseconds for general apps. Internet protocols turned atomic seconds into a utility every computer can drink from. The 24-hour day now lives inside packets, steady enough for science, safe enough for commerce, and simple enough for your phone to keep perfect time. Say Section 16 to continue with GNSS timing, how satellites carry atomic time to receivers, and why sky-based time rules everything from maps to power grids.
The world's clocks now agree by landline and radio. Satellites make that agreement portable. Global Navigation Satellite Systems, or GNNS, carry atomic time overhead and hand it to any receiver under open sky. Position needs time. A receiver measures how long signals travel from multiple satellites. Distance equals travel time times light speed. If the receiver's clock matches the satellite's clock, position and time both snap into place. Each constellation maintains its own continuous atomic timescale, tightly steered to the world's civil time. Navigation messages include the offset to civil time, so receivers can convert spaceborne time into the second used on Earth. A rooftop antenna feeds a timing receiver, which disciplines a local oscillator and hands out the synchronized second to networks and devices. Even a modest setup yields microsecond-level alignment for campuses, plants, or exchanges. Satellites carry multiple atomic clocks and broadcast precise orbits and clock health. Ground control constantly monitors and steers them. Receivers model delays in the atmosphere and calibrate internal path delays to squeeze out error. Multiple constellations, regional and global, mean more satellites, better geometry, and resilience. If one system is blocked by buildings or mountains, others fill the gaps so timing stays locked. Telecom base stations, power grids, and financial data centers phase lock to satellite time and then distribute it locally. Precision energy markets, wide area phaser measurements, and 5G/6G air interfaces all ride on this shared second. Where sky view is poor, facilities extend timing indoors with rooftop sources, fiber repeaters, and disciplined local oscillators, so machinery, cameras, and trading racks still see the same second. Space signals are faint and can be disturbed. Good practice layers defenses, spectrum monitoring, multi-band/multi-constellation receivers, authenticated augmentation where available, and stable local oscillators to ride through outages. Timing receivers discipline on-premise masters that speak precise time on the wire. Local networks then fan out microsecond-class alignment to switches, radios, and servers, keeping packets, trades, and sensors in causal order. With satellites, the same second falls everywhere the sky is visible. The 24-hour day now arrives by fiber, airwaves, and orbit, letting cities, ships, grids, and markets run as if they share one heartbeat. Civil clocks divide the day into 24 equal hours. Biology keeps its own beat. Human circadian rhythms run close to 24 hours and lock onto the light-dark cycle, so bodies and clocks stay in step. A master pacemaker in the brain coordinates daily rhythms in sleep, hormones, temperature, digestion, and alertness. Light is the strongest time giver, with meals, exercise, and social cues providing secondary alignment. Left alone without outside cues, the human clock free runs at just over 24 hours on average. Morning light resets it a little earlier each day, so it matches the planet's rotation without drifting late. Chronotype varies. Some people wake easily at dawn, others hit peak focus late. These innate preferences shape optimal work and study windows even when everyone shares the same 24-hour schedule. Rapid time zone changes or overnight shifts desynchronize the inner clock from civil time. Misalignment reduces performance, alters mood, and disrupts metabolism until light and routine gradually pull the clock back to local time. Alertness typically rises through the morning, dips after early afternoon, and peaks again before evening decline. Matching demanding tasks to your personal high alert window increases output with less strain. Regular bed and wake times anchor the clock. Irregular schedules scatter melatonin release, reduce sleep quality, and make Monday mornings feel like permanent mini jet lag. Bright outdoor light in the first hours after waking strengthens alignment. Dimmer, warmer light at night prevents delays. Blue heavy screens late in the evening push sleep later by signaling biological day. Daytime meals and exercise reinforce daytime metabolism and alertness. Late heavy meals and intense late-night workouts can delay the clock, making early rising harder. Biology prefers an almost 24-hour cadence, and civil time supplies the rails it runs on. Next, Section 18, Workday History and the 8-Hour Norm. How factories, lighting, and labor movements carve the modern day inside the 24-hour frame. Civil time fixed the 24-hour frame. Industry asked how to divide it for labor. The modern norm, 8 hours for work, 8 for rest, 8 for life, emerged from factories, strikes, and law. Early industrial cities ran on 10 to 16-hour shifts inherited from agrarian daylight. Long days strained health, safety, and families, while night lighting let mills stretch hours beyond dusk. Reformers popularized a simple formula: 8 for work, 8 for rest, 8 for what you will. The slogan turned an abstract demand into a memorable blueprint for dividing the day. Some trades negotiated shorter days first, especially dangerous building and foundry work. Shorter hours improved alertness, cut accidents, and sometimes raised output through steadier pacing. Citywide strikes pressed employers and councils to recognize 8-hour norms. Gains arrived unevenly. Some sectors adopted reduced hours, others resisted with wage cuts or speed-ups. Once mechanical hours disciplined shifts and timetables, fixed start and stop times became enforceable. Time cards, whistles, and standardized lunch breaks organized labor inside the 24-hour grid. Shorter, predictable shifts reduced fatigue-driven scrap and downtime. Regular rest supported training and retention, turning a moral claim into an efficiency case that managers could measure. Government rules gradually limited daily and weekly hours, banned child night work, and required overtime pay beyond an 8-hour day or 40-hour week, moving the norm from private contracts into public policy. A 5-day schedule concentrated labor into weekdays and created coordinated rest. For round-the-clock industries, rotating 8-hour shifts spread the 24-hour load without 12-hour fatigue penalties. 8 balances alertness, commutes, and coordination.
It fits transport, school, banking, and broadcast schedules, letting millions interact within overlapping windows while leaving evening and night to life and sleep. The 8-hour day didn't change the planet's 24 hours, it partitioned them. Next, section 19, 24-hour notation versus 12-hour AM/PM, why some cultures prefer one or the other, and how displays shape memory and mistakes.
The world agrees on 24 equal hours, but not on how to display them. Some read from 00 hours to 23:59 minutes. Others split the day into two cycles, with AM and PM. Counting the day from 00 to 23 removes ambiguity. Timetables, hospitals, aviation, shipping, military ops, and software favor it because 1840 is unambiguous while 640 needs AM/PM context. Many English-speaking regions still prefer the familiar two-cycle display. 7:15 p.m. reads naturally in speech and casual writing, and household clocks, school schedules, and TV guides often reflect that habit. AM means before midday, PM means after midday. The scheme splits 24 hours into two runs of 1 to 12. It's easy to say aloud, but it depends on remembering the label and can confuse around 12 o'clock. Noon and midnight don't sit cleanly in AM or PM. To avoid mistakes, use 12 noon and 12 midnight, or switch to 24-hour notation when scheduling critical events at the boundary. 24-hour. Europe, much of Latin America, much of Asia, transit systems, medicine, logistics, science, and computing. 12-hour, the United States, and other Anglophone contexts for everyday life, entertainment, retail, and casual communication. 24-hour displays cut misreads in high-stakes settings by making morning and evening obvious. 12-hour displays are fine when context is rich and the cost of an error is low. They add friction when context is missing. Morning, 01 to 11:59, same numbers with AM. Noon, 12 p.m. Afternoon and evening, 13 to 23:59, subtract 12 and append PM. Midnight, 12 a.m. Use 24-hour for international viewers, timetables, and any technical or safety-critical content. Use 12-hour for US-centric, conversational storytelling where spoken clarity and familiarity matter. If you show both, display 24-hour first with a subtle 12-hour in parentheses. Avoid all caps AM or PM clutter on small screens. Consider AM.PM or icons. Always use leading zeros in 24-hour 0705 to align digits and prevent misscan. Both notations narrate the same 24 hours. Pick the one that minimizes confusion for your viewers and the stakes of your message. Next, section 20, the closing synthesis and title options that answer who determined that a day has 24 hours in one compelling line. No single person decreed the 24-hour day. It emerged over millennia. Egyptians split night into 12 star watches and mirrored day. Greeks fixed 24 equal hours for calculation. Islamic scholars made equal hours practicable. European mechanics put them on the street. Railways, radio, satellites, and atomic clocks synchronized them worldwide. Egypt counted 12 by stars. Greece made hours equal. Islam made them accurate. Europe made them mechanical. Railways made them standard. Radio made them simultaneous. Atoms made them exact. 12 divides cleanly by 2, 3, 4, and 6, making two 12s easy to split and recombine. The format fit sundials, tables, bells, timetables, software, and global offsets. Once embedded in trade, law, and science, switching bases had more cost than benefit. Who determined that a day has 24 hours?
Civilizations did, step by step, selecting 12 plus 12 for practicality and later locking each part to an equal hour. The determiners are a relay team, not a single name. Civil time, 24 hours of 60 minutes each broadcasted as UTC. Earthlink, occasional leap seconds so noon stays near the sun. Distribution, networks, radio, and satellites deliver the same second to devices everywhere. Noon where midnight labeling in 12-hour format. Time zones and daylight saving changes. Leap second handling in software. Clear notation, 24-hour, explicit offsets, and documented leap second policy remove most errors. Close with a visual countdown from 24 to 0 as world scenes tick and sync, sundial to tower clock, telegraph office to radio studio, observatory to satellite dish, server rack to wristwatch, then a sunrise. The number never changed the sky. It changed how humanity moves beneath it. Why minutes and seconds are base 60? The invention of the calendar week and why it's 7 days. Could a base 10-day work and what would it break? Title: Who decided our day has 24 hours? The relay that built time. Alternate: From star watches to atomic clocks, how 24 won. Description opener: A 24-hour day wasn't invented once, it evolved. Egyptians split night into 12 star watches, Greeks fixed equal hours, Islamic scholars perfected instruments, Europe mechanized time, and modern systems synchronized it worldwide. This film follows the relay that turned the planet's spin into 24 equal parts. Subscribe for more.